In this example, we have an equation f of x is equal to 3, and I shouldn't include the a, I guess, in there, so let me erase that real quick. F of x is equal to 3 to the x plus 3 power, then minus 2. So this is an exponential, and what we're going to do is we're going to graph the parent function of this exponential, and then we're going to perform the transformations on it. So let's start with that. Let's just graph y is equal to, try to draw a better y for you. Y is equal to 3 to the x power. Notice we're removing everything except what makes this exponential, which is the base and then an exponent of x. The plus 3 and the minus 2, we're going to deal with those in just a little bit. If we graph y is equal to 3 to the x power, we can make a real quick table if you want. So we can do x and y over here. And there's a few things that we can do here. One anchor point that we want is when x is 0. Now 3 to the 0 power happens to be 1. That should be a 0 right there. Hopefully that's clear. And so the point 0, 1 is on the graph. Now this is not the graph of the blue function or f of x. This is a parent function. And we're just going to use this here, and we're going to shift everything here eventually to make that blue graph. X being 1 is another nice exponent to pick. So 3 to the first power is equal to 3. And then we have 3 squared for the next one. So when x is 2, 3 squared is 9. Now, eventually, you're going to get to a point where you don't have to make the table, and I want you to take a look at how these things are growing. So a nice point to pick first is this point 0, 1. That's on all of the parent functions, no matter what the base is. And the height there, the y value in magenta, is 1. If we move right 1, the next height is 3, which is 3 times 1. And then if we move to the next vertical piece right here, that vertical piece, if we move to the right 1 from 1, that would be 2. So the x value is 2 here. That height is then the height when x is 1 times 3 again. So whenever we move to the right by an x value of 1, the height triples or is multiplied by 3. It is not a coincidence that the base for this one is 3. Now you might be wondering, how could we graph some other points to the left without having to use the table? And we're going to take a look at this, and we're going to start with the vertical piece when x is 2, and that happens to be 9. So that magenta line here is 9 units. If we move to the left one, then the other height is 1/3 of the previous one. If we move to the left again, so when x is 0, we have 1/3 of 3, which is 1. If we move to the left 1 from 0, that would be -1. The height should be 1/3 of 1, or just 1/3. As we keep going, the heights all decrease by 1/3. And so what ends up happening is these points get super, super close to the x-axis, but they'll actually never cross the x-axis. And the reason for that is no matter what the exponent is here, so that's your 3 to the x power, whatever that exponent is, 3 to the x can never be 0 and can never be negative. In other words, like 3 to the -2 power is just 1/3 squared, which is 1/9, not 0 and not negative. So the shape of this graph is actually going to look a little bit like this. I'm going to try to draw that nice exponential curve here. And once again, this is just a helper graph or a parent function. I'm going to get rid of the magenta here so you can see this a little bit better, hopefully. Come on, erase you. There we go. And so we're going to use this now actually to graph the blue function. So if we take a look at the blue function, we're going to look at the transformation. So this one, the plus 3 up by the x, is going to be a shift left 3. And the -2 is going to be a shift down 2. So we're going to take every single point on this red graph, and we're going to shift left 3 down 2. So watch as I select the anchor point 0, 1, and we're going to move left 3. So we'll go left 3, and then we're going to go down 2. So the new point is actually right here. Now I'm going to get rid of those arrows so that we can see this a little bit more clearly. There we go. And so we can do this with every single point. And if we shift every point left 3 down 2, there's the point to the right of 0, 1. And then the point 2, 9 becomes this point right here. And then if you'll notice that this is kind of forming that shape that we're starting to see here, the red graph is just shifted over a little bit. And so the next point is going to be right down here. That's that point -1/1/3 that's been shifted. And then we'll continue to get closer and closer and closer to this line right here, which happens to be y is equal to -2. So if we draw this exponential function, it's going to look a little bit just like this here. Now that's a connector should be a little bit smoother there, I guess. And so we can also see here that this graph is getting closer and closer and closer to this line. So some people will draw a dashed line in here, and that's called an asymptote. There is a horizontal asymptote for exponential functions, but not a vertical one. Let's go through the key features. We can look at the equation, and also we can look at the graph to help us with these. So we're looking at the left side now right here. We're at key features. And the growth rate or decay rate, you can get that either by looking at the graph or looking at the equation. We can see here that the base is 3, which is bigger than 1. So this is totally going to be growth. If we look at the graph, if we're a point on the graph moving left to right, our y values are increasing. So the y values keep going up and up as we go to the right on either the blue or the red graph, but we want to use that blue graph. And the rate happens to be by a factor of 3. It's whatever that base is. So we're looking at the base for the growth or decay rate. The horizontal asymptote we said was y is equal to -2. And once again, we can also see that not only on the graph, but also in the equation. So that's right here. That's our vertical shift up or down. A horizontal line, if it's shifted up or down, will look different. However, if a horizontal line is shifted left or right, that horizontal line will stay the same. So we don't look at the shift left or right for the horizontal asymptote, but it definitely is tied into the vertical shift, which happens to be down 2. And you want to write y is equal to -2 here, reminding yourself that any horizontal line can be written as y is equal to -2. The domain for these exponential functions is going to be -infinity to infinity. Any real number is actually okay, and that's interval notation for saying any real number. The range, the possible y values here, are only from -2, and we draw a parenthesis indicating not including -2, all the way to infinity. So this means every real number from -2 to infinity, all of those are possible y values on that blue graph. The x-intercept happens to be this point right here, so I'll draw your attention to that. And there's an interesting way of solving for that x-intercept. I'm going to go back to the equation, remind myself what that is. So that's y, and I'm going to use a 0 here, is equal to 3 to the x plus 3. And then it's going to be -2. I'm using 0 for y because if you look at this point again right here, that x-intercept, the y value is 0. So what I can do is I can add 2 to each side. So I'll have 2 is equal to 3 to the x plus 3. These bases aren't the same, so this is a great spot for a logarithm. The base is 3. The argument is 2, and then the exponent, which is x plus 3, always goes on the other side of that logarithm. Then we're going to subtract 3 from each side, so we can write -3 plus log base 3 of 2 is equal to x. So what I'm going to do here is I'm going to get my calculator out, and I'm going to type that in, and that's from a previous lesson on how to utilize those logarithms. And I'm going to wind up with about -2.4. So this is about, x is about here. We can draw the wavy line, -2.4 if we use our calculator. So we've got -2.4 comma 0, and that's rounded. And you can see here that that's actually pretty believable. It's not exact way my graph is, but it's pretty darn close here. That could be negative about 2.4. The y-intercept, folks, is a little bit different. So I'll try to draw a line here for this one. The y-intercept is going to occur when x is 0. So let's see what happens there. So we've got y is equal to 3 to the 0 plus 3 power. Remember, the x is 0 for the y-intercept, then -2. So 0 plus 3 is 3, and 3 to the 3rd power happens to be 27, and 27 minus 2 is 25. So our y-intercept here is going to be 0. The x is always 0 for the y-intercept, comma 25. And if we look at our graph, we can see that that is believable. The graph would keep going up a little higher And even though my graph kind of squeezes in, I think the actual trajectory of this thing here would be about like that. And so it's believable that it would get to about 25 before it hits the y-axis up there. In terms of end behavior, as we approach infinity, so that's this part, and that's x approaches infinity, or all the way to the right, the y values approach infinity as well. They just keep climbing up and up and up. As x approaches negative infinity, we're actually going to approach our horizontal asymptote. And we can see that here in the graph as we continue to go to the left, 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 to the left. My y value is approaching that asymptote. So you're going to wind up with f of x approaching -2.